Good morning, everyone. I'm Shay, short for Shaghayer, which can be a bit tricky to pronounce. Today, I'm going to walk you through EVPN-VXLAN as a data center fabric solution. With huge volumes of data generated, moved around, and processed every second, underlying network must be able to meet our growing demands. I want to share our journey through thick and thin to move away from decades-old data center design to a more modern architecture. Here is a quick overview of what we will cover today. We will start by examining our current situation since we are in the early stages of implementation and haven't fully migrated yet. This gives you a snapshot of where we are starting from. Next, we will dive into challenges we face with the current technology and state. These are the pain points and limitations we are dealing with right now. We'll then explore how we are tackling these challenges, our strategies, and the steps we are taking to move forward. I will explain how we selected the product and technologies that we believe will address our needs effectively. We'll cover our planning process and how we are executing our strategy to ensure successful transition. And finally, we'll wrap up with the key lessons and insights we've gained so far. Before diving into challenges we face, let's start with a bit of background of our existing setup. We are managing a hybrid setup that combines a traditional 3-tier infrastructure using link aggregation and a Trill network. We have a substantial number of devices in operation, which requires ongoing management and oversights. Our day-to-day operations and troubleshooting depends on manual tools, and we are seeing a steady growth in the provisioning of services, which demands rapid scalability from our infrastructure. Our network visibility is distributed across several different monitoring tools, providing a diverse set of insights. At the moment, we are dealing with several key challenges that I will walk you through. As our network scales, managing traditional 3-tier architecture becomes increasingly complex. Additionally, while Trill is an IETF standard, not all vendors fully support it. This can limit our flexibility in selecting hardware or integrating of these technologies to the new hardware. The coexistence of these two technologies adds another layer of complexity. Currently, we handle tasks such as identifying affected product during field notices, security vulnerabilities, and bugs manually. And this process can be time-consuming and labor-intensive. Similarly, new challenges and deployment require manual configuration, which can be a considerable effort. Troubleshooting issues related to the current technologies, member links, control plane synchronization often requires vendor special privilege, which can increase the time and effort that we need for troubleshooting. Although Trill enhances loop prevention compared to traditional Ethernet, it still presents challenges that may require detailed analysis of its redundancy and loop prevention mechanisms. Regarding scalability limitations, I acknowledge that the traditional 3-tier network have inherent scalability limitations. While Trill offers improvement in scalability over traditional Ethernet by enhancing loop preventions and routing, it also has its own constraints. We are facing challenges with the network visibility as it is currently spread across multiple tools. And this distribution can complicate our ability to obtain a holistic view of our network performance. Our monitoring tools distributed across several dashboards, while this setup offers valuable insights, it can sometimes result in longer times for executing changes, troubleshooting, and service recovery. Last but not least, the pre- and post-upgrade checklist process is manual and can be both time-consuming and prone to errors. Each device required a detailed review, which adds to the complexity of the upgrade. Here is the approach we adopted for this project. We assessed our current situation, researched data center solution, and evaluated vendors' offerings through demos and documentations. We then matched these solutions to our requirements. Next, we moved into detailed planning and design, leading up to execution, where we will see the fruits of our efforts. During review, we agreed on 3 main pillars that technology of choice must deliver: technical, performance, and scalability. The solution must include redundancy and fault tolerance to ensure continuous operation and minimize downtime in case of failure, and it must support segmentation and service isolation to prevent issues from spreading and affecting other areas. Concerning performance, it must optimize traffic flow across the network, making the best use of available bandwidth, and quickly restore connectivity after failure to reduce downtime. In relation to scalability and flexibility, it must easily grow with increasing business needs. And it must effectively handle higher bandwidth requirements. Regarding architecture simplicity, it is very important that reduce complexity by simplifying network design and optimizing the number of components. Let's explore the data center evolution architecture from traditional 3-tier modern to more modern EVPN-VXLAN solutions. Traditional 3-tier architecture, scalability limitation is a big concern. Then link aggregation is introduced in 2018 to overcome the limitation of the spanning tree. Various vendors adopted this protocol under different naming to enable active uplinks and fully utilize available bandwidth by eliminating block ports. This technology is particularly effective in small data center environment where it optimizes traffic flow between clients and servers, ensuring efficient northbound and southbound communication. To address the challenges that 3-tier architecture brings us, a new data center design called closed network-based spine and leaf architecture were developed. The design overcome the limitation of previous technologies, providing more efficient and predictable handling of east-west traffic, ensuring low latency and high scalability. As you know that 2-tier class architecture, every lower switch, which is leaf layer, is connected to each top of the switch, which is a spine layer, in a full mesh topology. The leaf layer consists of access switches that connects to the devices such as servers. This spine is a backbone of the network that connects all leaf together. Each leaf switch connects to every spine switch in the fabric, and the path is randomly chosen so that traffic load is evenly distributed among top-tier switches. If one of the top-tier switches were to fail, it would slightly degrade performance throughout data center. If oversubscription of a link occurs, the process of expanding capacity is very straightforward. An additional spine switch can be added and uplinks to the leaf switches. If the device port capacity becomes a concern, a new leaf switch can be added by connecting to every spine switch and load the configuration. That's it. The next technology is Trill, introduced in 2010 using spine and leaf architecture, and it combines the best feature of traditional layer 2 and layer 3 technologies. Trill retains the simplicity and easy deployment of layer 2 environment while introducing a control plane protocol called Trill ISIS. This routing protocol ensures scalability, fast convergence, and the ability to use multiple paths similar to a layer 3 routed environment. However, it is a flood and LAN-based layer 2 technologies. ISIS determines switch ID reachability information, while end-host reachability information is learned through the initial data plane traffic flooding. As the number of hosts in the broadcast domain increase, the impact of flooding packets can become noticeable. Before diving into VXLAN, I will first provide a brief overview of overlay networks. Think of overlay network as a virtual network that operates on top of your existing physical infrastructure. It's like adding an extra layer of networking on top of what you already have. With an overlay network, you can create logical connections between devices, even they are physically located in different places. These logical connections are like virtual pathways that allow devices to communicate with each other seamlessly as where they were in the same local network, even though they might be in different geographical locations. This is useful in various scenarios, such as connecting data center, cloud services, and remote offices. VXLAN is one of the many available network virtualization overlay technologies. VXLAN is a tunneling technology that encapsulates Ethernet frames with UDP packets, allowing virtual network to be created on top of the physical. It provides network segmentation by extending the layer 2 broadcast domain across layer 3 boundaries, enabling communication between devices in different locations. VXLAN relies on flood and LAN-based forwarding, which means that it floods packets to all devices in the VXLAN segment until it runs the correct destination MAC address. As the number of hosts in the broadcast domain increase, it suffers the same flooding challenges as Trill spine and leaf network. To overcome the limitation of the flood and LAN VXLAN, vendors started using the new technology, which is EVPN-VXLAN. EVPN provides control plane and data plane separation and unified control plane for both layer 2 and layer 3 forwarding in a VXLAN overlay. EVPN automates the learning and distribution of MAC addresses, and it uses BGP control plane to distribute MAC and IP reachability information, reducing flooding and improve traffic efficiency. In summary, VXLAN is a basic tunneling technology creating for overlay network, while VXLAN enhances VXLAN with addition of EVPN to improve scalability, automation, and network efficiency. We compared the two latest technologies by mapping them against the captured requirement and rating those features accordingly. Both technologies offer high redundancy and fault tolerance, but EVPN-VXLAN is more flexible and scalable, operating independently of physical infrastructure. Trill supports up to 4,096 VLANs and uses VRF Lite for multi-tenancy, while EVPN-VXLAN, with its layer 3 VXLAN and flexible EVPN control plane, support up to 16 million segments to provide superior isolation and control. Trill improves traffic handling by multiple active paths, but EVPN-VXLAN offer greater efficiency with layer 3 overlays and BGP for optimized route selection and traffic distribution. Both solutions are scalable because they are using a class architecture. Both optimize bandwidths, but EVPN-VXLAN handles layer 2 and layer 3 traffic more efficiently. EVPN-VXLAN is simpler to integrate and scale, leveraging the existing IP routing and encapsulation technologies, whereas Trill involve more complex mechanism. In conclusion, EVPN-VXLAN is preferred for its scalability, simplicity, and effectiveness in meeting our data center requirements. We've documented the data center technology requirements, and I explained, I think, in the slide 3 or 4, but also we needed to address some operational requirements as some of our challenges were linked to operational aspects. We categorize requirements into 3 distinct areas: improve visibility, faster troubleshooting, and simple maintenance. We needed to have historical data utilizations to improve our visibility. We required better visibility into network health by monitoring environmental parameters and detecting abnormal resources and utilization. We needed statistics tracking, and also for faster troubleshooting, we needed a solution that could visualize the intended versus actual traffic paths to diagnose and resolve connectivity issues more efficiently. In regards to simple maintenance, we were looking to have improvement in vendor escalation, advisories, and receiving notifications, and upgrade and deployment assist. And most importantly, a unified management portal for data center operation. As we wanted to ensure our requirements will remain the forefront of our product selection decision, we are seeking unified management console that optimizes data center network operations. Throughout this presentation, when I say operation, I mean the entire life cycle, from initial setup and testing through automation, custom configuration, to ongoing daily operation and troubleshooting. Since the majority of our hardware in the existing environment are Nexus, which they are also supported, the technologies that we've chosen, we decided to move forward with Nexus for our hardware of choice. Consequently, for day 0 and day 1 operation, we found that NDFC, or Nexus Dashboard Fabric Controller, is best fit for our requirements, both in terms of technology and provisioning. And NDI, or Nexus Dashboard Insight, is well suited for visibility and managing day-to-day operations. Let's explore how data center fabric, how Nexus Dashboard Fabric Controller address the challenges we've identified. I want to cast your memories back to the challenges slide we said earlier. I hope you still remember some of the challenges that we discussed early on. Nexus Dashboard Fabric Controller offers comprehensive management tools for overseeing the entire network deployment. It's simplifying complex upgrade and operation tasks, and it's streamlined the management and deployment of software images, making upgrade more efficient and less error-prone. Hence, it's addressing the time-consuming challenge upgrade process. It provides unified graphical view of network health and performance, helping us to monitor and manage network more effectively. It also offers clear, layered visual representation of network topology, making it easier to understand and manage complex network structure. And it's helping us to overcome the challenge of limited modern network visibility. It also offers automation from day 0, streamlining and accelerating the deployment process by eliminating manual configuration and reducing errors that effectively address the challenge of labor-intensive manual deployment. With RESTful and JSON API, the solution integrates seamlessly with other systems, providing flexibility and scalability for management. And this capability enhances modularity and simplifies management, complementing EVPN-VXLAN technology and addressing network complexity and inflexibility. Let's dive into how Nexus Dashboard Insight addresses the remaining challenges that we've identified, similar to the previous slide, but we focus on day 2 operation. It offers virtual map of network layout, simplifying the understanding and management of complex network structure and improve overall visibility. The enhancement helps overcome lack of consistent monitoring practices that we've captured for our challenges. Additionally, it provides clear insights into multicast control planes and data plane statistics, allowing for a straightforward diagnosis and resolution of issues related to BGP, link aggregation, and more, and all from one single dashboard. And this feature helped us to address the challenges of limited modern network visibility. It utilizes flow telemetry and flow telemetry events to swiftly identify and resolve data plane issues such as packet drops and latency. The solution ensures accurate application of day 0 and day 1 configuration from NDFC, tracks network changes, and monitor health over time. And this capability helps us to address the challenge of troubleshooting and faults. Lastly, advisories and tools will keep us informed about security incidents, bugs, field notices, end-of-life, support announcements. And these notifications enable us to proactively maintain our security and compliance while reducing the need for manual daily operations. On this slide, we'll walk through how we are executing our plans. We are currently managing a greenfield rollout that includes 2 to 3 different projects. One project is entirely greenfield, while the other 2 involve creating a new greenfield environment and migrating from an existing brownfield network. As outlined in the approach slide, we began by capturing and reviewing our requirements, selecting the appropriate technologies and tools, and with these in place, we moved into detailed planning. We developed a meticulous rollout plan focusing on the design and deployment of EVPN-VXLAN fabric, and this plan covered comprehensive requirements gathering for each project, including performance, redundancy, high-level design that I'm going to talk about high-level design in detail shortly. Physical and logical topology, how many leaf and spine switches we are going to use based on our requirements, bandwidth and interconnections, we try to calculate required bandwidth and designing spine and leaf interconnections, considering factors like oversubscription and contention ratio. Following logistic phases, we proceeded to the detailed design stages. IP address planning for the services that we are going to deliver, and also IP address planning for the EVPN-VXLAN fabric by itself. Multi-site connections, planning for how we are going to connect our EVPN-VXLAN fabric from different data centers using our existing layer 3 infrastructure. Routing protocol, so many discussion around the underlay routing protocols to use OSPF or ISIS, that's a question. And also traffic encryption, implementing encryption measures like MACsec and CloudSec to secure the traffic between data centers. As soon as the rack design were ready, the data center team started racking and stacking the hardware. The next major step was provisioning NDFC and certifying deployment before it went live. From here, we will focus on the integration activities, including layer 2 and layer 3 interconnections, to link the new fabric to the existing fabric infrastructure in preparation for the migration that we haven't started yet. Here is a sneak peek of our high-level design that I'm confident that the engineers will want to see. This showcases the staging build for our greenfield environment, which follows spine and leaf architecture. In this setup, border gateways serve as the leaf for multi-site connectivity. We've aimed to create a staging environment that closely mirrors our production setup to ensure accuracy and consistency. Here is the core and edge side, or mainland and island diagram for our production network. As indicated, we chose not to use a collapsed spine design for this setup. Instead, we have allowed the spine switches to focus on their primary roles of managing internal routing and forwarding within a fabric. We have a separate border gateway to handle external connectivity to the broader layer 3 network. This approach was chosen to mitigate the risk of overloading the spine switches with both internal and external traffic. And by keeping these functions separate, we ensure that the spine switches have adequate resources such as CPU and TCAM dedicating to managing internal traffic without being burdened by external routing tasks. Based on our requirement, we selected leaf switches that support 28 by 100 gig ports and 8 by 400 gig ports for uplinks. For spine switches and border gateway, we decided to go with the same model. We chose a model that can accommodate 32 by 400 gig ports. For all of our core sites, all connections, whether between leaf and spine, spine and border gateway and inter-site connections, all of the connections will be 400 gig in the initial build. And this high-capacity setup ensures that our network can handle high traffic volume effectively from day one. As you can see, the diagram illustrated how we can scale a single site. By adding extra 400 gig uplink between spine and leaf and incorporating an additional spine, we can expand our site to support up to 14 leaf with 1:1 contention ratio. And this setup allows us effectively scale our network while maintaining performance and reliability. As our needs grow, we can deploy additional pod in a similar manner to further expand capacity and ensure the network remains robust and adaptable. As mentioned, we are still in finalizing the deployment phases, and we haven't started the integration and migration. We are diligently working to execute the plan as effectively as possible, and I look forward to sharing more about our achievements and any new challenges we encounter in the future. We began with layer 8 human, and we are now wrapping up with layer 1 physical. This slide is for those of you who might be interested in what you can see and touch. This is a photo of the rack that has the staging equipment installed, hot off the press. These photos have been taken a few days ago by our super organized field engineers. As we concluded our presentation, I would like to highlight some key takeaways that emerge from our journey. It's crucial to get a deeper understanding of the challenges of your organization and your team. A detailed understanding of these issues allows us to address all of the challenges more effectively and tailor our solution to meet their specific needs. When gathering requirements, it's very important to differentiate between essential features and desirable ones. You can never have everything because it's either costly or difficult. Apply a realistic lens. Always verify vendor claims through testing. Always confirm and test different permutations of features can work together and coexist. Don't assume. Integrating automation early in the process is key to streamlining operations and reducing manual interventions. While setting a high standard is very important for achieving excellence, it's equally crucial to remain adaptable. Flexibility allows us to adjust new information, evolving needs, and unforeseen challenges, ensuring continued success. Last but not least, build a strong partnership with vendors to leverage their expertise and support. Collaboration can lead to better problem resolution, faster troubleshooting, and more effective implementation. Thanks for listening to our story. I hope what I shared here can be used in your organization, and I look forward to any question and discussion you may have. Thank you.